In this lecture, we will apply the principles that we elaborated in the previous two lectures to engineering flow devices that operate at steady state. So in the previous couple of lectures, what we were looking at is how to generalize first law of thermodynamics to flow systems. So this involves getting a mathematical expression for mass balance, introducing flow work and enthalpy, which is important for differentiating a closed system from a flow system. And then most of the engineering systems operate at steady state. So that's what we did in the last couple of lectures. So this we want to extend to engineering flow devices, which are rather complicated. I mean, this is a turbine of a jet engine. This has, if you look at this, it has lots of parts and it does many more things. There's a combustion chamber, and then there's a turbine and so on. So this looks rather complicated. But what is within the scope of this class is analyze this in comparatively simple manner, so that the essence of the physics is retained. For example, most of the analysis we'll be doing will be on control volume, and there'll be steady state in these systems, and there might be some kind of work, for example, shaft work and electrical work and so on. The main thing which we will be emphasizing is to keep track of enthalpy that is flowing in and flowing out. Okay, at steady state, the overall enthalpy of fluids that is flowing out is same as the enthalpy that is flowing in. Okay, so that is the thing which you will keep track of during our analysis. But with that, this being relatively simple, we can get a lot of information from such an analysis. Nozzles and diffuses occur in a variety of situations, from jets to routine systems that we may encounter in day-to-day living. So the fluid mechanics of this can be quite complex. This is a place where incompressible flow is not applicable. So a lot of analysis involves compressible flow. A lot of very interesting analysis can be done from the point of fluid mechanics, but that is not what we will be doing here, because this class will restrict our energy balance to within the scope of first law. Okay, so there are two kinds of devices. One is a nozzle and a diffuser. So in a nozzle, the outlet velocity is much more than the inlet velocity. So when the velocity is high, the pressure is low. Diffuser, the opposite is the case. The velocity at the outlet is much less than the velocity at the inlet. When the velocity is less, the pressure is more. Okay, so it seems to raise many interesting paradoxes with respect to fluid mechanics, but those are the things which are beyond the scope of this class. You have to look at some textbooks on compressible flow to analyze this in greater detail. What we will be doing here is following an approach, especially for steady state system. In the next few slides, we'll be using the same kind of approach, because the system operates steady state. This equation is valid. So basically what we are going to bookkeep is the energy of the flowing system. The energy of the incoming flowing system is the same as the energy of the outgoing flowing system. So in this case, for example, there is no heat transfer from the system, and there is also work transfer from the system, and the potential energy can be approximately considered to be zero. Right, so that's not a these are not important things. So what we need to keep track is the amount of incoming energy that is involves the mass flow rate. Sorry, the mass flow rate times enthalpy plus the kinetic energy. Kinetic energy, in many instances, is neglected, but in the case of nozzles and diffusers, the change in kinetic energy is significant, and that has to be accounted for in our analysis. The mass flow rate of the incoming fluid is the same as the mass flow rate of the outgoing fluid, so that can be cancelled. So basically, there is an enthalpy change and the kinetic energy changes. Turbines are engineering devices which are of enormous importance. Okay, so our modern civilization depends upon turbines. So here, the entire thermal energy to generation of work depends upon operation of the turbines. So of course, there is the central significance of turbines is in obtaining work from the system. So most of the time, even if you just travel to Punky, we are having a thermal power plant, and there is a steam turbine which is operated to get work from the system. So what are the things that give rise to work? The things that are important are changes in enthalpy between the system, the fluid that is flowing out and the fluid that is flowing in. So this is the term that takes into account that part. And there is changes in kinetic energy, right? So kinetic energy also changes, and there is a change in potential energy. So if you see, for example, in the previous case, there was a diffuser which served a particular role, right? Here, what did we say? So the velocity is less, the pressure is high, right? So the diffuser is also integrated into the system, and it serves certain purpose. We are not going to analyze the design of a turbine, why the turbine is designed in this particular manner. All we are going to do is bookkeep these terms involving enthalpy changes, kinetic energy changes, and the potential energy changes. And then there is this another engineering device which is often seen is a throttling valve. Okay, so the throttling valve, what is important in a throttling valve is the enthalpy of the fluid on this side is the same as the enthalpy of the fluid on this side. Okay, so this is the main part. Okay, for an ideal gas, if the enthalpy balance is implemented, that would also mean that the temperature of the gas on this side is the same as the temperature of the gas on this side. This is the case for ideal gas. So in general, when the enthalpy balance is implemented, these are the terms that have to be equated, right? So for an ideal gas, there is a simplification, but in general condition for a throttling valve is this one. So this is something which you might have seen in your when you're having a shower in your bathroom. There is a pipe which brings in hot water, which is mixed with cold water, and then the mixed fluid comes out of the shower, right? So how do you keep track of the enthalpy balance? The incoming, so what you try to do is that it can be different depending upon the temperature you want. There can be different mass flow rates of hot and cold water, which these are the different flow rates, and the enthalpy balance involves, this is the enthalpy balance involves, these are the input enthalpy from these two sites, and this is the enthalpy that comes out from the shower, right? So that involves the mass flow rate of the cold fluid and the mass flow rate of the hot fluid times the enthalpy that is coming out, right? So again, these are all fairly elementary concepts which you should know how to implement in a variety of engineering scenarios. Okay, so these are all very common scenarios. Okay, so the more you understand thermodynamics, many more things are in the environment becomes more and more obvious. So this is the one final application which we will see, which are heat exchangers. Again, these are very, very important in engineering applications. So if you you would have seen, if you're in mechanical engineering or chemical engineering, you would have seen heat exchangers in your unit operation lab and so on. So in fact, behind the chemical engineering building, there is a huge real shell and tube heat exchanger. Of course, it's not operational, but you would see the scale, the physical scale of the heat exchangers. So here we want to bring out a particular point on how to choose different control volumes for the same application, and depending on your choice of control volume, different information is obtained, right? So here what do we see? You have water, and then there is a refrigerant, right? So this refrigerant is cooled from 70 degrees centigrade to 35 degrees centigrade. That amount of heat lost is taken up to heat water. Okay, so you are just presenting the pressure and temperature of the fluids. So again, the property tables are going to be very important here. This is a common refrigerant for which the property table is available in a textbook. Of course, water is presented in all property tables. So how do you first analyze? So there are two ways to analyze. So in this case, you can use this as the control volume. When you use this as the control volume, there is no overall heat transfer from this control volume, right? So everything is internal to this control volume. That is, the heat that is transferred from the refrigerant is given to water. But if you take this as a control volume, there is no net heat transfer out of the system. Again, there is no net work transfer out of this control volume, and there are no kinetic energy and potential energy changes. So what is the bookkeeping used for? So you bookkeep the amount of inlet enthalpy, that is the mass flow rate of water times the inlet enthalpy of water, mass flow rate of the refrigerant, and inlet enthalpy of the refrigerant. This is summed up and equated to the outlet enthalpy of water and the refrigerant, right? So that's what you try to bookkeep. As opposed to this control volume, this will give you certain information, right? So this information is what you're just saying, that the enthalpy loss due to from the refrigerant is taken up by water, right? So there is another control volume for the same system that can be considered, right? So here the control volume is just the refrigerant. So so with that, what do you say? Of course, in this control volume, there is net amount of heat transfer, right? So the heat transfer to water is from this control volume. So the heat transfer from this control volume is what is going to be used for heating up water, right? So you can use a different control volume and get different set of information. So if you think about what is the heat transferred from the refrigerant, that can be obtained by the mass flow rate of the refrigerant. So the heat transferred is, see, if you look at the, see, this is water, and this is the refrigerant that is being, refrigerant is being cooled, right? So here, mass, this is operating at steady state, right? So the mass flow rate of the inlet water and the outlet water is the same as, that is indicated by this quantity. Okay, so m dot w. Okay, so the heat that is transferred from this control volume is being used to change the enthalpy of water, right? So this is the net rate of heat transfer from this control volume is equal to mass flow rate of water, that is the same in the inlet and the outlet of the water stream, and the enthalpy change of outlet minus the enthalpy change between outlet and inlet of water stream. Okay, so that is the way you use first law of thermodynamics for analyzing this system. So the take-home message is you can use two different control volume and get two different information from such an analysis. So finally, there is one topic that is still left. We are going to implement first law of thermodynamics for flowing systems for some systems that do not operate at steady state. These are considerably less compared to other engineering applications that do operate at steady state, but still it is important to look at these systems that do not operate at steady state. That we will see in the next lecture. Thank you.